Few technical difficulties. We are ready to start. So welcome to the research seminar that is titled Sustainable Urban Traffic Planning, Reinforcement Learning Applications in Ride Pooling and Electric Vehicle Charging. We have two speakers today, Klavdiia Bochenina, and our other speaker is Sara Pyykkönen. But Klavdiia, you'll go first, and Klavdiia is a postdoctoral researcher in the Department of Computer Science.
Okay, thank you, Nico. Do we now broadcast the slides?
Yeah, we're sharing the screen.
Okay. So today both talks are from Spatial-Temporal Data Analysis Group of Computer Science Department. It is the group led by Professor Laura Ruotsalainen and currently consists of 13 researchers. And basically we are dealing with different kinds of algorithms and methods which are related to spatial-temporal data, related to urban systems, related to cities. We have a subgroup which is specialized in reinforcement learning for different applications. We have projects when we do time series analysis of NASA data, and we have one branch more related to computer vision things. So, as Mika said, my name is Klavdiia Bochenina, and my primary research interests were focused on three things. First thing is algorithms development. Second thing is data-driven simulation of real-world systems. And third thing, parallel and distributed computing. And luckily today we will have talk about all of these three things related to ride pooling. So I will give you some brief introduction why we decided to cope with this problem. We will talk about what is sustainable ride pooling, some brief introduction to reinforcement learning workflow, and then we will consider different components of the solution that we develop. So let's start. Greenhouse gas emissions, as you know, they disrupt the atmosphere, they lead to global warming, poor people health, harm wildlife species, and cause economic stress. And actually, there is a problem with greenhouse gas emissions in the European Union. And from all of the EU emissions, a quarter comes from transportation, with the majority of the emissions coming from road traffic. You can see from this diagram that notably transportation is the only sector with a drastic rise of emission in past 30 years. Addressing these challenges now in Helsinki, we have so-called a carbon neutral action plan. The goal is to make Helsinki carbon neutral by 2035. And two sectors for Finland, which are the most important, is transportation again, but also energy consumption of the buildings. It is electricity consumption and also things related to heating. If you compare this with what we saw for European Union, actually Finland is doing better than EU on average. Because we see some decrease in 10 years, like 15% decrease. But you can see that to meet the goals of this program, still there should be significant decrease. By 2035, decrease should be around 70% compared to the level of 2005. And in Helsinki, of course, we have different transportation means. For example, heavy-duty vehicles, public transport, also ships and boats, but still you can see that private cars, they contribute the most significantly to all the emissions in Finland. This is why in this program, there is a set of traffic-related actions. For example, we can create new charging points for electric cars, extending charging networks, so people will switch to electric cars. It can be some measures like creating new parking spaces and inventing some smart policies for parking pricing. Also, it can be promoting more eco-friendly transportation means like walking, cycling, and the use of public transport. Basically, these measures is actually the subject of our project that we were working for last 3 years. It is a project of Research Council of Finland, artificial intelligence for urban low emissions autonomous traffic. So the idea was to, by using the tools of simulation and artificial intelligence to predict and to estimate the impact of different measures invented with the appearance of automated and electrified transport. The interesting thing of the project, which was done by a consortium of 4 research groups from Helsinki University and Aalto University, was that we considered emissions arising from different levels. More on these levels here. First of all, we can operate at the vehicle level. It means that you can, for example, consider alternative fuels or more efficient combustion engines like hybrid cars and so on. You can promote electric vehicles, or for automated cars, you can also train the algorithms which allow for eco-driving strategies. It means that, for example, if you have plateaus of heavy-duty vehicles and you have several trucks coming one after another, you can train the algorithm for control of the trucks, like the sequence of accelerations and brakes, so the driving style of these automated cars would cause less emissions. Second thing is infrastructure level. For example, systems more related to Internet of Things and smart traffic signal controlling. For example, because if you can control how traffic signals operate at the intersection using some real-time data from the traffic, you can reduce the congestion and thus decrease CO2 emissions. My current talk is about fleet level. And the basic idea is that basically private cars are heavily underutilized. The average occupancy rate per private car is less than 2 people per car, so we have a lot of free spaces inside car, and of course, the more cars we have, the larger is the congestion and CO2 emissions. So in frames of this work, I was considering ride-pooling applications. We can define ride-pooling using this simple diagram. Basically, we will talk about taxi dispatching system. This one thing that passenger can share the rides. You see here that we have 2 taxis and 3 passengers. And if we pick up passenger 1 and passenger 2, they share most of their ways together, and it means you can use less cars and you can serve the same passenger with 1 car. So the overall system will have less emissions in a sense. A ride-pooling problem actually is interesting from the point of view of optimization because you have several sub-problems in it. The very basic problem is matching, that is how to pick up passengers or how to assign passengers to cars. In the systems like Uber, when both passengers and drivers are humans, there is always all the time rejection rates. And also sometimes different actors, they can bid for prices of the ride. In this case, we need pricing subsystem. Third part is routing. That is, you need to calculate the exact trajectory on the road graph. And sometimes also we think about repositioning. For example, we can send some taxi that is currently idle to the area with predicted high demand in the next hour, for example, and thus the overall system will be more efficient. In my problem, we were focusing on the matching because we consider the case with automated taxis, so we don't have the problem with rejection rates. And we assume that routing is performed with the built-in algorithm of our simulation tool. And idle taxis, because they are automated, they stay at the last destination points and can be used by next requests. One property of the problem that we work with on-demand setting, so we don't know which passenger requests are coming when, so we need to make a dynamic assignment according to the currently pending requests. Last thing about the problem itself, that it is multi-criteria because we have different actors in the system. We have passengers, and we want to think about passenger satisfaction during the rides. For example, minimize waiting time or deterrent distance. Our second point of view is about taxi fleet usage efficiency. We want to minimize the percentage of idle time and distance. And the third thing is the sustainability of the overall system when we want to directly measure CO2 and pollutants emissions. This part of the work was basically novel because usually researchers who work in the area, they say that, okay, we are optimizing for minimizing distance, and we assume that the pollutants will also minimize just because they have some linear dependence on the distance. But actually, our preliminary experience showed that this relationship is not so straightforward. So we suggest to model the emission directly with specialized emission models and consider it as a separate optimization criteria in the problem. Okay, let's go to the general workflow of reinforcement learning. Just to recap, in RL, our goal is to train the agent. In our case, agent can be, for example, a car or centralized dispatching algorithm, something like that. Agent operates in the environment. So basically, when we work with RL, we need a kind of simulation environment when agent can apply the actions and got some feedback from the system, which can be in a form of positive feedback, reward, or negative feedback, fine. All the process of training reinforcement learning model is a sequence of trials and errors when agent try different action. So it is a balance between exploration when he want to try new actions in new circumstances and exploitation because he want to use previously successful action from his experience. And the goal here is to optimize long-term reward over a set of actions because usually we work with some multi-step process, so it is not just a single action, but a sequence of actions. For example, this is the video which shows the results, some intermediate result of training of Pac-Man game. So environment here is the labyrinth, Pac-Man is our agent. The reward are food, and here he also have fine because he has enemies, these ghosts. So he needs to avoid the ghosts. Actually, this is pretty much similar to what we have in our ride-hailing application. If you imagine that Pac-Man is our taxi, if food is our customers that we want to pick up, and ghosts, for example, you can think of the background traffic because we want also to simulate the movement of the taxi in the dense traffic, and we need to avoid like different obstacles or not to have any accidents with other cars. So now you know what we are working with. First, we need the labyrinth. our labyrinth is actually a traffic model of Helsinki area, because the idea is to learn meaningful policies, rules of this taxi dispatching. We need to have an environment that resembles realistic traffic patterns within Helsinki city, and also some demand patterns, some directions where really people are traveling. Because, for example, in morning rush hour, like more people can come to the city center. For this environment, we selected open source traffic simulation software, which is called Simulation of Urban Mobility. And the process of creating this model consisted of two steps. First of all, we worked with origin destination matrix data, which came from HSL model, which is called helmet. This helmet model, it describes coarse-grained mobility on the level of the whole Finland. So basically, you have almost 2,000 big zones. So all Finland is divided at 2,000 zones. And origin destination matrix, it is basically just a matrix which contains a number of trips between different pairs of zones. And there are hourly origin destination matrices, so you have separate matrix for each hour. So first problem that we solved was how to reduce this origin destination matrices, because we need the same matrices, but only for Helsinki area. We developed special algorithm how to do that, and after that we arrived at OD matrices for just Helsinki regions. This work was published at SUMO user conference. Then, as I said, that the overall demand was really coarse-grained, we want also to check how good the traffic movement patterns are reproduced within the Helsinki, or can we improve what we have from origin destination matrices with additional data source. For this, we used traffic counting stations. Basically, Digitraffic provides very good API when you can extract by yourself traffic counts for more than 20 counting stations located. You can see how they are located on the map of Helsinki with quite good time discretization, I guess 10 or 15 minutes. So we used this data and we developed another algorithm for calibration of demand, because we observed that actually OD matrices that we extracted, they were not completely accurate. They have a big error, and we just made the algorithm how to make them more similar to the observed data. The result of this step was micro-simulation model of private car mobility in Helsinki city area with reasonable error. You see here we have 17% of MAP averaged over all traffic counting stations. Some of them are larger, some of them are smaller, but still it is, for this kind of studies, this is considered as good. And this model actually is available at GitHub. So in other work packages of the project, we also used it as a source of demand data for different models. Our reinforcement learning approach is based like on the following assumptions. Traditional algorithms for solving these matching problems, they either use some heuristic rules. In this case, you have some information about demand and supply, and you have some heuristic algorithm which outputs you which passenger should be sent to which taxi. It is so-called concrete assignments. So taxi 1 goes to pick up passenger 7. In previous reinforcement learning-based works, the same step was done just by the means of training reinforcement learning agent. So this is again concrete statement. What is the problem with that? That if we want to train the model for really like whole city, you see that you have a lot of taxis and passengers, and This increases the state and action space of reinforcement learning model drastically. So you really need train it for a long time until it converges. This is why we suggested another vision of the problem. We still use reinforcement learning, but we use it in a meta-heuristic setting. So we think that we can have arbitrary dispatching heuristic, which is parameterized by vector of parameters. For example, these parameters may be maximum capacity of the taxi, it may be maximum pickup drop-off distance or something like that. And we train reinforcement learning agent to select these parameters rather than to select exact like assignments. In this way, actually, computationally, it becomes much easier. Here I have some video. You can see how the trained algorithm works for one of the area in Helsinki. So blue dots are passengers, yellow are background traffic, and green triangles are taxis. And you can see that taxis are picking up passengers. I don't know what the scenario is here with which capacity, but basically they can pick up more than 1 point. So this is also how Sumo simulator looks.
And what was the difference between yellow and green?
Green are our taxis that we control, and yellow, they represent background traffic. So it is just cars that travel somewhere in the area, but they do not pick up passengers. Because basically we studied these scenarios when, for example, we have 100% traffic by private cars, but then we say, what if 10% of the trips will be served by taxis? But the other 90%, they are still there because, how to say, in this way, you can simulate, for example, situation of congestion in the city. So they are still presented and influence also the movements of the taxis. About the implementation, maybe a little bit. So to work with that, we created gym environment, which uses Sumo simulator is good because it has special kind of API, which is called Tracy API. And you can connect to the running simulation, and through the API, you can get all the parameters of the fleet of taxis, of the trajectories. And for reinforcement learning, actually, it is very good because you can calculate your rewards or whatever you want at every time step. Let me show you just some examples of the results. The interesting thing here is that actually we need to develop not only our algorithm, but also the baseline for the algorithm, because we did not have comparable competitors who work also with the same like reward formulation. But we arrived at the point that when we tested again the baseline based on some exhaustive search or action space, our RL solutions was in all of the cases better, or at least at the same level as best of the baseline. And maybe right picture is more interesting because you can see how RL thinks. I said that it optimized for long-term reward for all simulation period for 1 hour in a sense. And you can see that baseline was more efficient in the beginning of the simulation, but for peak hour, reinforcement learning worked better exactly because it learned that it needs to accumulate some capacity, not to serve all the requests straight in the beginning when they arrive, but accumulate some capacity for the peak hour, and for overall like horizon, it performed better. The other example of the results is when we analyze the let's say right pooling metrics, not the reward itself, because for example, these plots for 3 group of metrics that I showed before, it shows how these metrics vary with the level of supply in the system. Percentage of taxi is the parameter which influences how many taxis you have. And for example, you can see that regarding the emissions, there is some tipping point after which increasing the size of the fleet of the taxis, it does not lead to like improving CO2 emissions, but it leads actually to worsening CO2 emissions compared to the baseline. Baseline was the case when we have only private cars to serve all of the demand. So basically, with the help of the algorithm and tool that we developed, we can understand these like border conditions after which ride pooling will be beneficial in points of view of emissions. And for the same conditions, you can check how happy will be passengers or how taxi fleet will be used. Finally, about the scaling. Even our algorithm was more efficient than previously developed. Still, reinforcement learning may be really slow to converge, especially for stochastic problem, large-scale problem, and problem with sparse rewards. The example that I showed for this area, it requires approximately 1 day of training at the server for one instance. But usually when we work with RL, we also want to train for different sets of parameters. We want to test different hyperparameters. Sometimes we want to experiment with different ways of creating a RL problem. So basically, it is a lot of work. And that's why we decided to also exploit massive parallel architectures. The idea is really simple. We don't touch the training, so all training is performed sequentially, but we can launch several simulators, several environments, and we will have several agents just gaining experience more quickly in several environments. And that's what we've done with this algorithm at LUMI supercomputer, which according to the most recent edition of top 500 is now 8th in the world. It was released in November 2024. And it is the fastest supercomputer in Europe with 380 petaflops peak performance. And we worked with CPU partition. Basically, we experimented with areas of different sizes inside Helsinki. And maybe the most interesting part of this work, which we just submitted to PDP conference this Monday, was that we did not only tested the experimentally how it the execution time for different number of cores, but we also invented some simple theoretical parallel performance model. In the rightmost plot, you can see like dots, they are measured execution times, and lines, it is a theoretical model fitted, which actually explains the data pretty good with error around 15%, and a reasonable parallel efficiency for our case studies because we have one sequential part here with the gradient steps that we cannot parallelize, and still it was like 0.35. So maybe the main outcome of this talk is that if you want to create reinforcement learning model which need to operate with some real world system as an environment, you need 3 components. You need to train the environment first, and it is always better if it is grounded at some real data. So the more realistic environment you have, the more reasonable policies you can train from that. Then, of course, algorithm itself, and also different techniques for training accelerations, for example, parallel computing. We were able to find some conditions. Using these conditions, the right pooling becomes beneficial from the points of view of emissions. And now we are looking forward to continue with this work for example, with upscaling of the results for the whole Helsinki and larger areas with custom CO2 emissions model created by atmospheric scientists for Helsinki region, or, for example, to rethink reinforcement learning part, we are now working on the generalized matching algorithm, which will work not only for my taxis in the city, but also for like physical robots delivering things in the shopping malls. I think that's mostly it. Thank you. And question, please.
Yeah, thanks. Thanks, Klavdiia. Yeah, let's take some time for discussion and questions and comments, either online or here in person. Who would like to go first? Please.
What kind of state space did you use?
In this problem, the state space was really simple. It was the parameters of current demand, so the number of pending requests in the system. At least the example of the parameter.
Number of where cost?
Yeah.
Location would that be work?
In this case, in the example that I show, the idea is that we control the parameters of dispatching algorithm. So it is not the algorithm. Let's say we control, we set, for example, for 10 minutes, the maximum capacity of all the taxis equal to 4. And then we have some dispatching heuristic, which like, for example, it already had some mechanism for picking up customers based on the distance, but we tune the parameters of this heuristic, and this heuristic, it works with locations. Basically, we didn't compare so far because at the moment the idea was to test the validity of the approach. That's why we compared it to the like really near optimal baseline. The other thing why we did not compare with, for example, deep pool algorithm, it is that the goal of our project was to get some meaningful results for Helsinki area and to work with the demand from Helsinki and also Helsinki road graphs and so on. And most of the state-of-the-art algorithms, they are tested at New York taxi cab data sets from Manhattan. So we haven't plans to do this actually in frames of the second work that I mentioned, to apply this and to compare like this reinforcement learning part, but we haven't done this so
far. When do you expect that this automatically driving taxis could be a reality in Helsinki? And is it now more of a question about technological development or political permissions?
Well, basically, I have to say that in carbon neutral Helsinki action plan, you have two scenarios that they studied, and you can find even expected percentages of automated like an electric cars like rates in these documents. So they already made some forecast how it should be in, for example, 2040. Yeah, 2040. So I guess it was something like for automated cars, maybe like dozens of persons in like dozens of years. But I don't know. If you had the document with scenarios, maybe I can check and tell, for example, after Sarah's talk.
Yeah, the documents over mine, but I cannot remember.
Because actually for the for our project, we also developed a set of scenarios, including foresight scenarios with parameters that we want to study with the set of stakeholders, like from city authorities, from HSL, to understand which parameters we do need to use in our models to answer the questions for example, if the population of Helsinki will be increasing by 150,000 of people in a year, how it will influence. Or, for example, if we will have 1/3 of all the cars electrified, how many charging stations do we need? Because current, for example, charging network, it will not, cannot serve such amount of cars.
Is the main advantage of these automatically driving taxis in comparison to traditional taxis, or maybe kind of like peer-to-peer ride pooling, that the rejection rate gets lower?
Yeah, also this, because they cannot say I don't want to like drive you.
Are there some other advantages?
I think from the point of view of a real, how to say, deployment in a city, maybe considering the fact that still algorithms of automated cars, they are not perfect, it can be a really good thing for example, last mile. So not in the crowd city center when we have a lot of traffic, but for example, like in some suburban areas. But yeah.
Facebook?
Yeah, I guess. Yeah.
Check out the whole document and what the audit I was looking at the table.
Yeah, for example, we even found the document. But yeah, for example, in the scenarios that we derived from like regulatory document for 2030, in the scenario with a high penetration rate, it was 8% of commercial taxis, like driverless. And for 2014, in the high scenarios, it was 70%. I don't know how realistic it is, but it is always like for us as a modelers, it is always interesting to check like significantly different conditions. Because at least then you can give information to the stakeholders. What if, like, I don't know, we have all the taxis like driverless? Because I know that sometimes even non-existent means of transportation, they are also studied, for example, some flying cars, or I guess there was even pilot in Finland for parcel delivery with drones or something like that. And simulation is a good thing because we can study even this kind of phenomenon. Actually, this may be a problem because not all people would like to share the rights, but I guess in the existing studies, usually this demand, it is somehow balanced or promoted by the price of the ride, because some people, for the same price, they will not go with some random person, let's say, but if it will be significantly cheaper, for example, some people may use it.
But has offered this already? I don't know, maybe not in Finland, but at least in the United States several years ago.
Yeah. I guess there have been such kind of things, but for example, in our case, at least according to current experiments, maybe it will be even not mostly about like classical taxis, like with 4 passengers, but maybe about some shuttles, because you need to have certain level of capacity within the car. So it may be some thing which is not so much like the classical Uber services.
Yeah.
Why LUMI? Like, is the environment is it running slowly? Or...
Basically, it is, as you saw, the parallelization is quite nice because it is just like vectorized environments. So mostly it is related to the fact that we want to train not a single instance of the model, but we want to train a lot of instances for different areas of the city and also with different scenarios. So the demand is different, like the, let's say, if you have, I don't know, 5 parameters that you want to explore, and with each parameter with the grid, you can have already like hundreds of instances that you want to train. And then LUMI is good thing for that, because you can just do it faster.
But for a single.
For a single run, let's say for the let's say for area 1, I guess it is less than 1 day. For area 3, it may be like 40 hours, something like that, in a sequential version. So still it is, for example, now we have work on this upscaling of the results, and the idea is that we want to get our emission results from our model for, let's say, 10 areas in different parts of Helsinki. And then our colleagues will get these emission results and somehow approximate like for the whole city. And this means that you need to train already 10. And if one is trained for 40 hours, it will be for 100 hours. And if you want to train for different parameters, it is even longer. So in this sense, LUMI is good.
Very good. So thanks again, Klavdiia. Really interesting topic.
Yeah.
And our next speaker, indeed, is Sara Pyykälä. Her title is Smart Electric Vehicles and Charging Stations.
Hi. I'm going to give an outline of my research that's been split across several papers currently, and explain how it started and where I'm currently now. So it's a little bit easier to understand where it's going. And everything starts with the project that Klavdiia is already telling about, that we were hired for. So I will sort of. So the consortium about how to design the city layout so that the carbon emissions would be from the traffic would be reduced. I had a little bit more specific research question when I was hired. So my question was specifically about the electric vehicle charging stations and their locations and how they should be placed in the city of Helsinki. This is quite a fact question when you start to look at it. So the very first thing when I came into the project was to ask, like, what is actually electric vehicle in a very bare bone idea. So electric vehicle is actually a spectrum in the sense that you have normal combustion vehicle that runs with a gasoline. But electric vehicles can actually tap into the electricity in 2 different ways, 3, but the third is not really popular in Finland. So the very easy way is that they fully replace the gasoline with electricity, and the car runs with that. The other version is called the plug-in hybrid, where you have both the gasoline engine and the electric engine, and the car can use both for moving out. The third, which is not really popular in Finland, but which you might encounter somewhere else in the world, is that you have a gasoline engine, but it actually uses electricity to power up that engine, therefore saving the gasoline. It's usually called basically like a just hybrid, not just like a plug-in hybrid, as a way to say that you don't plug it in at the station like the normal electric vehicle cars. The second question, and then I started asking like how many of the electric vehicles we are going to have in Finland and in the project. We heard this is the most recent statistic that's come around in Finland. So roughly 10% actually of all the cars in Finland, and it's a higher concentration or density in Helsinki specifically. Also, I believe that's due to the urban demographics according to the hypothesis. So it's easier to use electric vehicle here than in the north of Finland. The second question was that, okay, now we know what the situation is now, what it's going to be by the time we actually go to the simulations, because we were not really targeting the moment now, but more like the moment from 10 years from now. So that's where the Carbon Helsinki 2030 initiative came in, that Klavdiia said that they had a goal that they would reduce traffic emissions quite drastically. As actual exact numbers, it would mean this. So 600,000 tons of CO2 emissions was measured in 2015. And from there, they calculated that they want to reduce it by 496 tons. For contrast, it has been estimated that 1 ton of CO2 is actually 138 meat meals. So that's a lot of meat meals for you to go for. How's the fleet? Well, that's a little bit more difficult. So in 2030, the EV share about all the cars, it varies. The Carbon 2030 initiative said that the business as usual scenario is 14%. I think we are gonna catch on to that quite quick, a little bit quicker than 2030, maybe even. Then the higher estimates, for example, by Motiva, which is about the motor traffic in Finland, they said that maybe even 60 to 80% could be handled and could be done. EU said that maybe if we get a full ban on gasoline vehicles, maybe even 100% at some point. that's a little bit optimistic to say 2030. It's going to be a little bit down the line, maybe 2050. So
can I interrupt a little bit? Is the idea of the ban would be that you would sell new traditional cars, but people would still have their own.
Yeah, they would still have their old cars, old gasoline cars. So all the new production of the new car, gasoline cars would be stopped, and they would have to try and transfer to the electric cars. And then the idea is that depending on the policy incentives to change the cars, people would drop out of their gasoline cars and go to the electric vehicles. So that's what really drives the share. But it's estimated even that if the EU does this ban on the gasoline production, it would not take this. It would take quite a long while to people transfer. So these are the most realistic estimates for the 2040 goal that we are looking more mostly in the project. So that's it. Well, yeah. Then the second question that I asked for my question, that there was also a term called charging stations that I didn't really know. So I started asking, like, what's the idea of it? Who are the vendors of the different charging stations in Finland? Turns out there are quite many different commercial ones. So, for example, K-Lataus, Lidl, Kempower, that have their own. But there are also more public ones like Helen and Virta, who are also a little bit interchangeably together. And also there are a lot of private charging stations in the flats of the apartments on the cellars and so on. But as an example, how many we actually have? We have this map of Helen stations alone in Helsinki. The current number is 113. That's quite a lot. Then the second question, then I started asking, like, what's the difference between these stations? So, and I discovered that there are quite a few. The very first that comes to usually to mind is that, okay, what you can also see in the map is that they have a different power output, the power. So you can have anything usually between very small things like 10, 12 kilowatts all the way to the 300 and plus. But most common is that it's a little bit in between, but also for the driver, we can see that there are different block types. So not all cars use the same block type in all of the stations. As an example for Helen, again, because that's most to know about, we have an alternating current station with 22 kilowatts of power and a type 2 plug. CCS coming, but type 2 is still the most common in Europe, and especially here. And those are basically the blue stations in the map. And the yellow ones in the map is the more powerful ones, and red ones as well. So they start from 50 and go up a little. Then I had realized at this point, when I was going through all the statistics and the initiatives and ideas, I was understanding the field map, so to speak, where we are working with. And I started asking, like, how to actually solve the problem that we were looking for, so the layout. So the very first thing that I realized based on the statistics that I had is that electric vehicles actually do not generate carbon dioxide emissions from tailpipe, as generally looked at. So asking a question how to reduce carbon emissions by affecting electric traffic actually came a little bit uncommon. So there is, of course, the emissions of the electric production from the factories. but the consortium was not considering that in the project scope, and we didn't have any scientists to consider that. We were just considering the tailpipe traffic emissions. So I was also assuming that I should just only consider the traffic emissions, and it led to the point that I'm actually looking at zeros in the output of my problem. And that's a little bit the problem. Then I started running around and realized that, okay, well, the electric vehicles are still part of the traffic, so everything is not supposed to be. So then I started thinking that how to turn this around is that, okay, what if the electric vehicles are actually incentive for the auto drivers to drive around? So we still have the combustion vehicles in 2040, and the electric vehicles can still be a diverting factor for those. So, for example, if there's a jam, would you like to drive into it, kind of question? So, and that's the point. So, if the electric stations are, the charging stations are really the points that every driver should, at some point of their car life cycle, go to, and that means that the cars are going through some kind of like a flow cycle all the time, and the combustion vehicles would probably steer away from those, and that's what we can actually study. So, this was the point. So I realized that, okay, we can simulate the different charging station locations this way. We can assume that the electric vehicles have an impact on the combustion traffic that we're looking for. Then the second question was, of course, that even if I do build like a digital Helsinki simulator and put different station locations there, does it really correspond to what we are seeing in Helsinki right now? So no matter what I do. The locations could be taken as a realistic one, so we could look for criteria and different sites where to put them. But the really question what I would look into output is the drivers, of course. I would need to see where the traffic goes and why the drivers pick these stations to go to. So this was my conclusion. I should try to understand the drivers and why they do what they do. Not just the routing choices, but also like the choices of why here, why now, like the origin and destination. But you answered the question with the origin destination reduction, which is now the basis. Now it was just a question of what stations the drivers actually use. For this, we started to turn to help for our stakeholders. And we found Helen, which is why I've been using Helen's examples. So we requested Helen and explained the problem and asked if they had anything that could help us with this problem. And they came back with a data set. That was really nice. So what the data set was, it was event records from all of their stations between March and September 23. So using a mock example of the table, and the number of events varies a little. I think the overall number was somewhere around 200,000 before I started looking at all the records. And there was a little bit of also like technical issues. Some of the records I had to a little bit go for under that. I think it ended up that I took out around 10% out of the end date. There were also like a missing, erroneous start and stop times in the sense that the drivers didn't stop at all, for example, the stations. But it told me a very good question. So after I could have this data, I modified the research question. Now I had an understanding what the drivers do, but in a sense, but I couldn't still tell what drives the drivers in a sense to this stage. So I could tell the big trend of the Helsinki. I could know exactly that on this date we had this many events, but could I really see like the different factors influencing the choices? And this is where the simulation came in. So reinforcement learning was all about having these actions, having the simulations to try them out. And I decided that the best way to approach this question was to recreate the driver in the simulation and start tweaking them a little and see what they did. So the problem. We get a driver and we'll build a twin in the simulation. We build a set of different factors that we could imagine them optimizing for in the choices. We simulate them as they drive around the city. They think about where they're going with their car. They think about the price of the charging that's there. They think about how long it takes to actually go to the stations, what's the queue there? Do I even get a seat? And what's the remaining charge? If you have a full charged car, you probably don't need to really go to charge. But in the sense, we can say that they can do this action. Okay, if you had a low charge, there was a station nearby, the price was affordable, there was no queues. Why not go? You had the time, 30 minutes, make a detour, and go back to your destination after that. So that's how the state and action goes. We see the drivers make their choices before they go to the trip because they understand the constraints they are working under in the real world. And we just see the stations they pick and where they go. But workflow actually keep game after that, kind of this. We have the Helen data. We can analyze that through very extensively to understand the trends and the localities. We can go to simulation and tweak the drivers around. We get the kind of a similar data set from the simulation as well. And we can compare that to the Helen data and see whether it's the same. Well, simulation is running LUMI once more. The idea was for that to really go through with this, we needed the whole city of Helsinki, and that's a little bit too heavy for a single computer, the laptop, and for the handle. We need a cluster. So the second one was that also the side point, but we also wanted to build a carbon emission estimation model for the computations running LUMI. That's another project for us. What's that? Another reason to use it. We decided to go for simultaneous 1 week. According to the literature, this is the maximum time that the drivers can actually go without a charge. They go over a 1 week charge in Germany. So we decided to see if this is the same for Helsinki as well. We are currently running the simulations, and we are going through a little bit of the results. So I cannot share the full output, but I can share you one preliminary finding, which is really easy to understand soon enough with the demos. So the current number of Helen stations, 130, is not approximately enough anymore when the share of EVs is 60% in the upper echelons of the predictions. This is both through the fact that we use the current network of Helen stations, and we didn't put our own station up to speed so far. But also through to the fact that the stations are underutilized for now, but they can only support to a certain limit. So in order to actually reach the Carbon 2030 initiative, the finding would be that the network has to be expanded and increased to support all the EVs that we want. But for now, I thought it was way too boring for me not to give you the full results of my work. So I designed that we could take a look at the Helen data through the visualizations I derived and the findings I saw there. And I could also show one iteration of the emission tool that we have for the spatial simulation of the outputs. I think that's nice. I'm gonna show you it in a very easy way. It's basically in my Chrome and in here. So the first thing from the Helen data was this. So I just decided to plot a little bit different ideas and see where it goes. But I have to share my window, it seems. Let's see. Here and switch and the whole screen. And yeah, and this one as well, yeah, because I don't know where is it go. Where did it go? I have to probably exit that. Yes, there we go. And here, there, now we have it. First thing I started asking, is there like a specific date that the drivers would like to use their stations? And so I plotted the histograms of the different number of events everywhere. So this is the whole of the 66 some ones put into the weekdays. And what I saw quite immediately, I also verified, there is not much of a difference here. Drivers are actually pretty consistent from day-to-day basis in a weekday ideas. Lovely, isn't it? So those are very similar, actually, all in all. We can also see a little bit of a trend here. So and I categorize the power rating of the different stations. And we can see that the less powered up stations are the ones that people frequent most longest. It's actually hilariously long. This is a clipped day. The maximum stay I could find from the data was 11 days. So people can really park over long, but for statistical purposes, we have to call a few outliers here. So that's why I clipped it into 300 minutes. But we can still see that there is a little bit of tail, and people are still doing kind of a long stays at the station. But we can also see that for higher power station, the median is more closer to actual like a hour of stays or so, or less stays. It runs around a little. Second point, is this the same true for like a monthly variations? So I plotted the monthly variations without regards to the weekdays, and it was the same again. People are super consistent with the monthly ideas. It was really fun. If somebody asks why this is here and not in the other legends, it was because the Helen network actually changed during the data that they sent. So they built new stations which had over 200 kilowatts of power in Aalankatu, and they were not there in other months, so that's why they're not visible there. But again, I could see that, okay, cool. There is some similarities again in how people actually use them. It's a little bit more like a Gaussian process, Gaussian like a bell curve in a sense for the low, like there were less powered up stations, but a little more skewed for the ones that are higher powered. And it was true again, according to the statistics test. You could see a little bit deviation in the bell curve here. What really was fun to see was actually this. So I saw that I just meant for the whole daily, like idea about how the occupation ratio goes. So how many stations and connectors are actually reserved at a given moment. We could see that this follows like a kind of a stable baseline. There is not a really big like change anywhere else except here. So this is actually midsummer when I started checking the calendar. It was really nice to see. So that the drivers are actually so consistent about driving apparently outside Helsinki that we see already a drop in the usage of stations around that weekend. Otherwise, I cannot see. There was not much. We were theoretizing a little about what drives the change here exactly, so that the yellows drop. But it seems like it could be related to this, but we couldn't find like a really enough significant difference in statistic tests to explain that. So it could be that there is the commercial network of other vendors have expanded and some drivers have moved on to those. It could be also the explanation. We only see Helen here. And then the final. This was the one final picture I had was really nice. So I figured out what happens in if you would think about like an average Monday in a station, what it would look like. So I took all the events and I took the occupation ratio again. So how many connectors are reserved at a given time, and asked about just the times, the day-night variation. And we can see a very stable pattern here as well. That's been proven in literature a couple of times. People use them mostly in the work time during week. So the peak is roughly around from 8, 10 to over like the mid and night hours of 10 p.m. and 8 p.m. and it starts to drop. So people really park during their work days apparently to the station, so let it be here and are happy with it. And they move on during the night. It doesn't drop out fully, so I assume that some people are just parking over the night. Maybe they are in a holiday or they don't need the car, and that's okay, and they're willing to pay. That's another explanation for the occupation ratio, but it seems like there is a little bit of like a work traffic here in here. So, and this was like the target that we were really hoping for to find in the simulations, that we could see that some of the people are like work-based travelers with the cars and park here, and some of them are more like a domestic or like a somehow private car owners, that they just leave the car there because they don't really need it at the moment. And we went out to look for this. But for now, I wanted to also show you another, a little more interesting tool example. So we already saw like one example about the slow in run, so I cannot show you that again, but I'm going to show you the second tool because the original question was again about the emissions, and the emissions are not really nice like that in a in a histogram format. So there was another tool that we came up with to see like the spatial resolution, and there are also the different emission types, because Summa can also generate outputs for any number of like emissions. For carbon dioxide was not really interesting for the electric vehicles, but so I decided to put just for show the noise estimation of the Summa. There is also several other parameters here, like for example, if you have multiple time steps, would you want to see the average or the sum of the different emissions? I'm using a sum, and also here's the time step interval. We are using 1 hour of data in here, but you could say that, for example, if you want to aggregate it in a 15-minute intervals instead of 1 minute, you could go here. And after that, you can see the spatial resolution. The network used was CAMPI, as you can see. We have a little bit of our slice of CAMPI, and we can see how the time changes here. And when you go over, you can see that, okay, you can see that what's the noise amount and how many vehicles are driving, what's the time step and so on for 1 hour and how it's changing. You can also zoom in a little and see like the different road networks and where are the highest points of noise, for example. The drill down, this is a little bit on beta, but you can also see the rundown of the whole network, like what's the noise here and the color coding for average emission, in this case, the noise factor, and also the ratio in terms of like how many cars are actually driving here. So they're like the temporal scale of basically what's going on in that road. And to change it from the whole network, you can also go to the road level with this, okay, and you see where it goes. Okay, there are definitely somewhere nearby traffic lights. You can see that it's spiking up and down. And same here. So we can see that, okay, the emission for the noise is a little bit less for fuel than electric, and electric actually generate more noise, according to the models of some. And we can then start to figure out if there are specific heat spots here, like what's really driving them when we look at the outputs of the Summa and the GUI of that. That was really all. So currently we're hoping to get more results from the LUMI simulation and hopefully getting there. And the reinforcement learning model is a little bit technical, but you're happy to ask questions about that. So I will show you the summary for that. So the starting was that we should place the charging stations in Helsinki so that carbon emissions from traffic are reduced. And we started approaching the question and trying to understand what really drives the drivers to choose the stations they do. And we found some unique patterns to the behavior from the Helens data. And we are currently trying to recreate them and see how the drivers change their behavior if we change a little bit of the objectives and the parameters driving the different factors in there. And that's all.
Thanks.
Okay.
Yeah, time for questions and comments again. And maybe can I start with a few probably easy ones. The first is that how can the noise level be higher for the electric vehicle?
That's a really good question. I also
They are like completely silent.
Not okay, not always true. No, actually, it depends a lot on the driving speed, from what I've understood, and I assume that's the real reason. So when in higher speed, it starts to differentiate a little. I've understood for the combustion vehicles, but for the lower amount of like power in the engine, it actually is higher in the how to say tyhjäkäynti. It idles a little the engine. And that's what makes the most noise for the electric engine, and that's how it goes. But this is a really interesting result I was also looking at in some more models, but through reality, through this, it has been also tested empirically, and especially in the urban districts, like where the people are in the residential areas where drivers are driving slowly, it shows.
Then my other question, if I may, you're talking about understanding the drivers, and I was thinking here, do you have an idea like who are the people or what are the kind of like cases where people choose to use these public charging points, because they are, I guess one of the main or one of the big motivations for people to get an electric vehicle is that you don't need to spend money on gasoline.
Yeah.
And which is kind of expensive, and instead you can get electricity, which is almost free. But it is almost free when you are charging at home. Whereas if you are charging at some of these like commercial spots, it can be quite a bit more expensive. So.
Exactly. Yeah, that's a very good point. And that's why, and also if you ever see in Helen's pricing card, you can say that it's not really easy to also estimate the price. So yeah, it's a point that some of the ongoing existing literature also studied like home charging and so on. For now, we were studying mostly about the big networks because it's still a quite small like a share of the home chargers. I think when I was reading literature, it could be around 10% in some of the here, but I don't know about the numbers in Finland. That was Germany, I think, again. So for why we chose Helen here and the other vendors is because their networks are so much larger than ever it could be for the home private owners. The private owners are a trickle in ocean, but Helen's and Kempower's charging stations are much more efficient than the ones that usually are installed in homes as well. And that's what also people tend to use a lot. So the idea is that not also one other like a result that was kind of found that people can also use them in like tandem. So people charge at home, but they can also charge at workplace, and the workplace will have again probably like a contract with Helen or Virta Kempower, a similar vendor, to have that charging station there. So it was more incentive to say that we shouldn't like move the responsibility of instances in the network for the private owners, because that's also like an economic situation we can't really handle. But our stakeholders are committed to having and meeting the Carbon Helsinki 2030 initiative, and they wanted more ideas how to do that. So that's why I decided to focus on the public charging points. Exactly. So in the future, I hope that both parties can actually start it and go for it. But the exact factors for the who chooses public and why somebody chooses home, there is no clear answer for me. So and in the literature, I think so. It's mostly a matter of convenience, I think, for the people to choose.
I had one bit of a stranger question as
Go.
well.
No, go.
Some time back, you might remember we were talking to a radiologist from University of Eastern Finland. And he was actually saying that in the future, like most EVs will can be charged like directly wirelessly from the streets. They're like,
yeah, that's true. Yeah, that's true. Yes.
And I was wondering, first of all, like, would that bring the problem here altogether? And do you know is that's like that technology, like how far is it? Like, is it something that's like coming up soon or maybe never?
I can definitely answer to that. So I heard about it. So the first idea would be that you would have a big lorry or a truck that you could drive the car into on top of it, and there would be the plugs and like a charging map or something like that could connect to the car and then start transferring the energy. So in a sense, it would be a mobile actually a charging station. That's also another idea. So it's a really interesting idea. I don't know how long the technology is currently. I'm going to say it takes a while. But in a sense, I guess this could be modified to also include the idea because the lorries would have to be situated somewhere. And if they're not, then they are moving cars. So they would be part of the traffic in a sense. Yeah. But it's a really interesting question. I'm also looking forward to it.
But I know we definitely need to ask the developers of Sumo simulators to add some functionality for them because how they don't have flying cars or wireless charger.
No. Right now, yes. The Sumo is still looking at charging stations as mostly static parking areas.
Yeah.
And so, when we were talking, he was actually talking about this as sort of also as a problem because he says that there are some like radiation related issues there.
I can imagine, yes. Yes. Anything else? Apparently too expensive. Thank you for your attention.
Yeah, if no more questions, then I guess it's time to conclude the session. But thanks again to both of the speakers and everyone in attendance. So thank you.
That's it.